Vincent? Okay. Good. So, as already announced by Klaus and Jörn, this afternoon we will have an introduction to the gammaSTAR framework. So, this will be first a very rough introduction about the project and what's behind the gammaSTAR framework, what was the reasoning of developing that. Then we will combine it with a lecture about different MR sequence designs. So we will show some of the artifacts that Jörn already showed in actual MR sequences that are designed to also be used for clinical imaging. So that's maybe the main difference between the teaching tool that you used until now, which is more for rapid prototyping and prototyping of ideas, generating different contours very, very fast, and a sequence development tool that's really developed for creating MR sequences that are then used for clinical scanning, so that you are able to control the whole sequence, the whole protocol, protocolization, changing parameters while at the scanner. So, and by the way, my name is Daniel Hoinkiss, and I'm, I think it's called a principal scientist here at Fraunhofer MEVIS, and I'm leading all the activities regarding the gammaSTAR framework, which also means that I'm not the main developer anymore, but there are many colleagues that put a lot of effort into this framework. So the reasoning behind it was really to get rid of this heterogeneity of MR sequence development. So in the past, if you wanted to develop any kind of MR sequence, you would either do it in the GE or Philips or Siemens proprietary environments. They are quite complicated to use, C++ based and hard to learn, but they also have unique sequence description languages. So that means that it was not able to create an MR sequence for Philips and then go to an MR site and just test your sequence. So it would need a complete re-implementation of this sequence. So what that also means is that there are redundant copies of exactly the same MR sequences with little differences in details, so that if you think about going to a clinic that that has different MR systems, for example, of different vendors, you cannot be sure that you in the end really get the same comparable image results because of slight differences in the sequence implementation. So what we had in mind is to create a unified standard for MR sequences, so a description language that is generalized, so that all the MR physics is saved in this one generalized file and then brought to the MR systems, and they hold a very, very lightweight software driver that then translates this general MR sequence into the hardware-specific control commands. And this, in the end, would then result in the exact same MR physics being played out on the different MR systems, but creating a harmonized and comparable image result. And the nice thing is that you can actually share MR sequences between sites of, or not of different vendors, but using MR systems of different vendors. So we came up with a framework that we now call gammaSTAR. And the idea is really to have a web-based intuitive front end that then in this illustration here has these adapters going towards the MR system, and all the hardware specific details, they are really only in these little software drivers, and everything that's being implemented is in a generalized way. So one very important topic that we had in mind, and that's also where I joined the project. So before joining the gammaSTAR project, I was a PhD student working on prospective motion correction. So I was the one that was then responsible to make prospective motion correction possible in this framework, which means that there would not be a pre-calculation of the whole sequence, and then the pre-calculated sequence would just run at the scanner, but you need to be able to react to motion during the scan, which means that your sequence has to be run in real time. And then what we added and what we will see later is also something called what we call gammaSTAR reconstructions, which is also a standardized interface for raw data to reconstruction conversion, meaning that if we unify the MR sequence side, we still have the image reconstruction that for different vendors, for example, everyone by now knows that Philips is very, very much smoothing all their images in the post-processing. So by applying different post-processing and reconstruction modules alone, the image results are hardly comparable. But by standardizing that also, we get very harmonized images. So it all started in 2015, which is quite a while. So that's where I started with my PhD thesis, and then like 4 years later, I joined actually this project. It was funded by Fraunhofer, so a Fraunhofer internal funding, and was then until 2021 supported by Fraunhofer until we got a quite large funding by the Federal Ministry of Education and Research in Germany. And I want to go through this timeline by showing some of the milestones and alongside that explaining different features of the software. So I think 2 years after starting the project, we got the first images on Siemens MR systems because we own a Siemens MR system. So we started developing the driver development for Siemens MR systems, and by now are supporting all the different software and hardware models of the Siemens Healthineers MR systems. I will probably go over. Okay, let's directly jump into how this driver for Siemens would work for the user. So if you are sitting in front of an MR system, I don't know who controlled an MR system in the past already. Okay, then what you see here is basically the positioning module. So there you have the 3 orientations, sagittal, polar, and axle, and you have the measurement queue. So here is where you put in all your sequences, and then they will be one after the other. So what we just do is to load our driver software, which is basically written in the vendor's proprietary language, so that it's allowed to be run on a Siemens MR system. I hope you can hear that. So we just start with our default game, which is always a simple 2D slice acquisition. It's doing all the adjustments and the shimming, so making the magnetic field homogeneous and then acquiring the image. And it's also directly integrated into the viewer software of the MR system. So we can also use the whole UI of the MR system, so changing the position of the slice that we acquire. We wait for the adjustment. And we see that another slice position was acquired. So it's exactly the same workflow right at the MR scanner as you're used to with any other vendor-based sequences. The only difference is that we have this little pop-up UI, because normally every MR sequence would be one vendor sequence. So you would pull over or drag and drop your different sequences into this protocol queue. But in our case, we only have one sequence driver, which is able to communicate with our gammaSTAR backend. And then we can use this driver to select all the different sequences, all the different parameters. So it's basically just a connection to our whole gammaSTAR backend. So we can go in here, change parameters. For example, we just changed the number of slices to 3, and we directly get the visual feedback here in the positioning that, you know, okay, these are the 3 slices that would be acquired. We will start the scan and see all 3 slices being acquired directly in the vendor's interface. So if you, as I said, we have access to the whole sequence library. So we have this simple drop-down menu having all the different MR sequence options that we have. So we can simply change the sequence to a, in this case, pulsed ASL sequence. We will then accept it, see that it changes now to a 3D slab. So a 3D volume that's being acquired. It's not a 2D sequence, so it does not show single 2D slices, but now it's a 3D sequence acquiring a whole volume, which is exactly represented here in the vendor's interface. And also the measurement time is being shown here, and the sequence will start. So who is used to ASL probably does know that sound, so that's an ASL sequence, and that was also one reason behind getting this all calculated in real time, because if you think of a very, very complex MR sequence like ASL, a 2-minute ASL protocol, if you want to pre-calculate the whole sequence, that would probably take 30 seconds. So you would press you would press the button to run the sequence, and then you would wait for 30 seconds, maybe 1 minute, and then the acquisition would start, and you really don't want to do that. So it should start immediately with the first events in the MR sequence, and then while running the sequence should then calculate all the remaining hardware events. And the other thing is, if you pre-calculate a very complex and long sequence, even the MR systems with a lot of memory will at some point just stop working. And this point is earlier than you would expect. So after, let's say, 20 to 30 seconds of calculating a whole MR sequence, the scanner would just stop working. So we need to keep the amount of information in the memory of the MR system as small as possible. So that's also a reason why we only pre-calculate a very, very, very small part of the sequence. And when the sequence is running, we calculate in a buffer fashion all the rest after each other. So just some example images. We have by now quite a mature sequence library. So the typical clinical sequences, balanced SSFP, flash sequences in 2D or 3D, T1 MPH, WARE, FLAIR, so everything that you are probably used to when reading about MR exams, and then also physiological MR sequences like arterial spin labeling, diffusion-rated imaging, and also MR spectroscopy. So if you not think about MR imaging, but voxel-based MR spectroscopy, where you then get these spectra about a specific voxel that you've read out. So we published a online version of gammaSTAR, which is the we say the old version. So we will work today and tomorrow with a new implementation of the whole framework, which will be published end of August. So I will just jump over that. Yeah, this was then published in magnetic resonance and imaging back in 2018. So that was really the backbone of the whole framework. And just 2 or 3 months ago, we published another paper showing the new iteration of the framework, also to magnetic resonance and imaging. Yeah, as I said, 2018 I joined the project, and then my task was to make it possible to also acquire images in real time, have prospective motion correction applied and different interactions, real-time interactions to the MR sequence. So if you look at these results, it's basically what Jörn showed with a subject in the scanner moving throughout the time of the scan, and then you try to follow the subject with your imaging plane. So this is a, I think, 5-minute acquisition. At the top, the subject was told to not move, but there were no head restraints. So, and without head restraint, you can think about 1 millimeter or 1 degree in rotation of motion per minute. That's basically our experience with MR sequences like diffusion radiated imaging, where we have very, very strong gradients and we really feel the table shaking throughout the measurement. It's even more. But yeah, in this case, it was like a rotation of 2 degrees and also a translation of 2 millimeters. And if we overlay in this time series of API acquisitions, the first with the latest image, we see that we get quite a difference when subtracting these images. And then yeah, the lower part shows the exact same with prospective motion correction applied, and you see that there's only a subtle amount of motion left, which could also just be noise of the motion correction data. We also did some other real-time interactions to the MR sequence in a project where it's about interventional MR, so MR-guided therapies, where we try to steer interventional devices within gammaSTAR during the measurement. For that, we had some phantom experiments, also animal experiments, but here it's like a acrylic glass 3D phantom. So we would insert an interventional guide wire that's equipped with so-called passive MR markers. I don't have a picture here, but you can maybe see it here. So the red curve is the reconstructed guide wire that's detected, and below that there are some kind of round black blobs, and these are coming from a coating of the wire at these positions that create negative MR artifacts, so basically black holes in the image. And yeah, we track them, we reconstruct the guide wire, and tell the gammaSTAR software where the slice position should be moved to, and with that we can follow this guide wire with only one 2-dimensional slice throughout the measurement. At the start of 2021, we got the first images on GE. Just some example images. Currently, we are working with the TOPI framework, which was developed at the University of Michigan, and we are currently working on an own native driver implementation. And yeah, that was supposed to mean last month. So we were in New Zealand, I think 3 or 4 weeks ago, and did our first acquisition on GE systems. then following that, we had a very, very nice collaboration with the University Hospital in Leiden. So the Leiden University Medical Center, and there Martijn Nachtigall started developing a Philips driver for gammaSTAR, which went quite smooth. So these are some technical details, but we can show basically the same video I showed for Siemens now for Philips MR systems. It's probably not so important what's down here, but here you see this pop-up window that we already saw. Oops. You could select the sequence, change all the sequence parameters that would change the timing of the sequence to generate new contrasts. And even though I do not hear any sound, no.
The next scan will take less than half a minute.
Okay, that was very, very quiet. I don't know if you heard it, but it was basically the same sequence that we heard in the Siemens video, and now also showing the generated image. So we did some traveling head volunteer studies, comparing the different vendor results. I will maybe go a bit faster with these slides. So it's basically giving us, well, by now it's possible to run the exact same MR sequences we run on Siemens, also on Philips, also the very complex ones, arterial spin labeling, etc. So we can really compare the image quality here. But then we immediately saw that there's a very, very large difference coming from the reconstruction, because for both systems, Siemens and Philips, we use the vendor reconstruction, and there are quite a lot of differences in there. So we try to use a, let's say, abandoned open source image reconstruction framework, and got some results, but also started to thinking about an own implementation of a standardized image reconstruction platform, which Jörn will show in some minutes. So that's then just a comparison of arterial spin labeling. So even these a bit more complex sequences, long sequences, are able to run vendor independently on multiple systems. And I don't exactly know the year, but it's probably 1 year ago where we started the first 3 vendor comparisons. So we did it with MR spectroscopy, because it's quite a nice quantitative way to compare different image outcomes. So on the left, you see the sequence diagram for a single voxel spectroscopy method called STEAM. And on the right, you can see the different spectra coming out of this sequence, which are very, very comparable. And MR spectroscopy is quite sensitive, because you need a very, very strong water saturation, because if you see that, you think, okay, we have this great spectrum and we see all these peaks, but in reality, there would be a water peak like to the roof. So we need to get rid of that. So have a very precise water saturation, which means that all these MR sequences really need to be played out exactly as they were implemented. Yeah, and in May, so 2 or 3 months ago, we then published the, let's say, framework description in magnetic resonance and imaging, which is now really an explanation of the whole framework, including the driver, the real-time interface, and everything that's related to gammaSTAR. We will see that later. And then here we started to redesign the whole software. And that's also what's installed on your workshop computers, and what we will jump into in a second. Now, so what we want to do is to combine it with a, let's say, lecture style of explaining different MR sequence designs. So yesterday and today in the morning you learned about how to prepare the magnetization to get different contrasts, but mainly it was with acquiring EPI images, because it's a great way to, in a fast way, acquire a two-dimensional image. So whatever you do before this EPI readout, you can play around with that and you can change the contrast and then just get a 2D image of exactly that contrast that you prepared with your RF pulses and gradients. But we also want to show you a bit more about MR sequence development, all the different sequence types, and also applications where you to use them. So they are highly or high resolution structural MR sequences, but they are also very, very fast MR sequences, and they differ from 2 minutes per volume to, like, I don't know, 100 milliseconds per volume. And there was a lot of thinking going into the sequence design throughout the last 30 or 40 years. And we just want to show you the variety of these different readouts, trajectories that we use to cover the case space. And I think so. I cannot close this presentation, so I need to skip that. That's for tomorrow in the morning. And I want to hand over to Jörn to also give us an insight about the gammaSTAR recon work, because that's actually already installed and working with the framework. So all the reconstructed images that you will see in the hands-on part, they are basically an MR sequence in the gammaSTAR framework being sent to a simulation interface that reads the MR sequence, simulates the case-based results, so the frequency domain results, sends the data to Jörn, so to the reconstruction server. The reconstruction server, based on the sequence information, would read out what's needed to get a correct representation of this image, which is not always the same. So you cannot always just do a Fourier transform and get the image, because there are many, many acceleration techniques or correction methods involved. But they are automatically detected by Jörn's reconstruction interface, and we will always get a nice looking image back. And that's also why we combine it with a talk about the single reconstruction steps, so that you do not think that it's always as easy as getting the image back, but there's a lot going on in the background.
Yeah. Yeah, so we can really go quickly through these slides that we created sometimes or some time ago. Yeah, so basically the idea is that if you really want to do vendor-independent MR imaging, you can't really take your MR sequences as an independent thing from the MR reconstruction. So basically MR imaging is MR sequences plus MR reconstruction, and this whole thing is your imaging method. And as Daniel explained, you have different MR sequences which require different reconstructions. And more severe, you have different vendors which have their own image reconstructions implemented. For example, as Daniel already mentioned, there's Philips and Siemens, and maybe one vendor applies more smoothing than the other. So if you want to compare those images, it's basically not really possible, because you don't really know what happens inside of those black boxes, which are considered the MRI reconstructions. And that means that, for example, even if you have the same MR sequence using gammaSTAR, which is applied on these two large full body systems, you have these two different reconstructions. So you get two different images. So in actual cases, it's not that severe, but maybe they will differ a bit. And in addition, you have other systems like such tabletop MR systems, which we also have, where there might not even be some sort of image reconstruction. So you would need to come up with that on your own. So it's true for the tabletop systems and also for the simulator that Daniel already mentioned. And for those, it would be really nice to have the exact same reconstruction framework, which is capable of reconstructing data from these large systems, from simulators, from tabletop systems, so you're really sure that the exact same reconstruction steps are happening every time. And that is why we basically started developing this reconstruction framework for gammaSTAR sequences. And if you want to do that, you need to somehow define a standardized way of transferring data, which was already proposed back in, I think, 2015 or 16, which is the so-called ISMRMRD format. And this ISMRMRD format is basically a first attempt to provide a standardized way on how to transfer and store MRI data from different sources. So the basic concept is that you have a so-called ISMRMRD data set, which consists of a so-called header file and a data file. So the header file basically consists of information which belongs to the principal setup of your experiment, like matrix size, field of view, the desired reconstruction size of your image, the field strength and stuff like that. And you also have like raw data samples, which come with individual data headers. So this basically encodes different flags, like to which line in K-space this sample of raw data belongs, so how many channels were active and stuff like that. And yeah, then you have the data samples, which is basically complex numbers, so the actual data of your experiment. And the nice thing about gammaSTAR is that it's basically directly compatible to this ISMRMRD standard. So if we have, for example, this EPI sequence, and we look at one event in that sequence, it basically has a so-called corresponding raw representation, which contains information about that event. And there, all these so-called ISMRMRD parameters are basically encoded. So we have direct access to that, and we can utilize that to provide the correct reconstruction based on this information, which is contained in this raw representation. And so within our group, we basically started to develop different tools. So at first, the main reason was because we have so many people with different expertise, like motion correction or arterial spin labeling or patient-specific adaptations of the sequences and stuff like that. So the main idea was to collect all that in some sort of toolbox so people could benefit from that and jumpstart their own research by just using what is already there. And at one point, we basically noticed that we have everything which is needed to build a full reconstruction server, as it is running on Siemens systems or Philips systems. So that was the origin. We had this reconstruction toolbox, which now basically fires the whole reconstruction server, and it contains algorithms for parallel imaging. So for example, we have 2D grapher algorithms included, we have 3D caipirinha, we have different stuff for coil sensitivity estimation, if you want to do it reference-less. We have this propeller technique, which I also showed, so to be robust against motion. And we also have some processing tools, so the idea is basically the same. We have a lot of expertise within our group. We want to collect everything, so we basically have tools for arterial spin labeling, processing, for automatic quality assessment, and also some helper functionality, so foreground mask extraction and stuff like that. So basically all of that is then collected inside a so-called Docker server, which is basically a way to provide programs to different locations or systems. And inside that, we have our reconstruction toolbox and this processing toolbox, and this simply runs at all of your systems which are in front of you. And in combination with the gammaSTAR sequence, all different systems basically send their data to that reconstruction server. So no matter what the source is, so tabletop systems, simulators, full body systems, they are all encoded using this ISMRMRD standard. We have different reconstruction tools. So these tools automatically decide whether they need to be applied or not based on these flags which are contained inside the data. And then in the end, we get images. So we had some basic examples or comparisons, which are quite, or some months old right now, where we compare to the Siemens reconstruction, and we saw that it worked quite nice. And we also have some high resolution ASL images acquired using a pseudo-continuous 3 GRASE propeller sequence from gammaSTAR. And so that's basically from the reconstruction side. And we will learn a bit more about the reconstruction in an interactive way when we skip through or click through the protocol. So we will see different sequences and have a bit deeper look into how these sequences are actually reconstructed on these MR systems or within our reconstruction server then.
Okay, so I always have to wait until I'm unmuted. So as already mentioned, we will now have a more of a higher level look into the framework, showing the different sequences, the protocol interactions, the simulation, try to reconstruct some of the artifacts that we already saw, and then tomorrow in the morning there will be, if you like to go a bit deeper and continue exploring sequence development as you did with the teaching tool, we will also do that in gammaSTAR in a way where then we would really create MR sequences that could be at the MRI system, also having flexible MR protocol parameters that would then at the system based on the clinical need change the controls on the fly. If you are not into that, tomorrow there would also be a tour to the MR system. So whoever of you is quite new to the field, that might be quite interesting. So we have a Siemens 3-tester MR system right across the campus. And we also will bring Lucas, 2, 3, 20?
So we will have upstairs
2 to 3 of our tabletop systems. So maybe just to quickly show. So these are, in contrast to these mock-up MR systems, just having some audio driver and LED lighting, actual MR systems for standard power supplies. So you can just put them, that's why they are called tabletop, you can just put them at the desk, use a normal power supply, and they actually have the same hardware as a large MR system. They are about 30,000 euros per device, and we were lucky to get the funding of acquiring 5 of them. It's mainly for educational purposes, but it's also to have something to test MR sequences without going to the large MR system, because sometimes there are more than one studies running at the system, so it's quite busy, and then it's a great way to have, as a first step, a simulation environment to actually see what your sequence does, then the tabletop systems, and then if that's all working, going to the large MR system. So that would be the third thing that you could look into tomorrow. Okay, so you have these workshop notebooks, so you can follow me along. You can also just listen to me and follow what I'm doing here, but you actually have the software installed, the same version I have. It's in the desktop directory called TACTIX Summer School, and then there's just a batch script called one gammaSTAR, and it should bring you to this main page. So we will show different types of sequences, give a rough overview about the framework, so you can definitely just do exactly the same. You can play around with the protocols, you can continue tomorrow to do that. Just give me a little feedback if the software was starting, or if on your local device there's some issue. Okay. So if it's not starting, you need to double click Docker desktop because it's a Docker-based installation, and it might be that Docker did not start on your machine. So I started it in the morning, but sometimes software does not last for more than 6 hours. So what's happening if you double click that is that it will run 4 different Docker containers. So who knows Docker? Okay. So it's basically 4 different systems that are containerized so that we actually can deploy the installation as we have it on our system. So it's a standardized way to deploy different systems. So it's basically each of these Docker containers is, I think, a Linux system with a specific installation, specific software, and then of course our software installed on top of that. So that's just running in the background, and there's, for example, one Docker image for communication of the simulation environment, the reconstruction environment, and then the whole gammaSTAR front end. So what you do not have, or let's first jump into any sequence. So you see this load existing sequence button. So we will use that one today on the existing sequences, and we'll go to the flash sequence first. Flash. Are there different flash sequences? No. Okay. Oh yeah. You can also do the demo flash, but that's not a clinical sequence. So that's just a very simple, minimal example of the typical flash sequence. So what you not have is basically this network cable to these little mock-ups. So we actually went to the RSNA, so the largest radiology conference in the world, and Fraunhofer MEVIS has a booth there, and they asked us, I don't know, 1 month ahead of the conference, if we have anything to show which is not software displayed on the monitor, because it's quite sad to always just have a display and a mouse and a computer and a keyboard and showing software. Because we are a software-based institute, of course we have software, and we cannot bring our large MR system, so we were asked to have something for demonstrational purposes, and came up with these mock-ups. So what they are basically representations of real MR systems having real software drivers. So we can just use our, in this case, flash sequence, send it to these MR systems. We hear the actual sound of the sequence, which is not recorded, but calculated from the diagrams or the hardware events. So if you change the protocol, it will also be changed. And we see that a lot, maybe during the next hour. And
sorry, how did those options pop up there?
for the no-feed scanners?
No, we only see SIM. That's the only thing that we see.
Yes.
This is how it okay.
Yeah, because you're not connected to these systems.
Okay.
But you have the simulation, which is unfortunately not giving me any image. Give me a second. Okay. I just need to restart my Docker. 1 second. So I would have followed, I should have followed you along and also start the software. Okay. Okay, I'll just check if everything is running, and then we'll continue with the design of the sequence. Let's see. And so we can select any of the different devices. It's our cheapest version of having a multi-vendor setup in the building. So you could imagine having a GE, Philips, and Siemens scanner, and that's the mock-up version of that. So I could select just one of the systems together with the simulation, and then send it just to one of the systems. Okay. So what's happening there is really if you go to the graph symbol here, to the sequence plot, you see the actual sequence diagram of the sequence. And what's happening is that all these hardware events of this very simple sequence are being packed into a representation being sent to the simulation server. And then from there, the actual case-based data will be transferred to the reconstruction server and getting sent back as a just PNG image. Together with the DICOM file. So you can also just download DICOM, but I don't think you have a DICOM viewer on there, but it's actually a minimal DICOM image because it's just a simulation. It's missing all the patient information, whatever. So we just put some random information in there, but it's a DICOM image and it's compatible to DICOM viewers. Yeah.
Which is a different phantom.
Yeah. Yes and no. There are different phantoms in the Stocker image, but it's one phantom pre-selected for this course.
Oh.
If you want another phantom, I could just put it into the Python code that's running in the background. But yes, there are, I don't know. So it's an online database. These are not our phantoms. So there's an online database called WebBrain, and they have phantom data or in vivo data with T1 maps, T2 maps, and all these different parameter maps that the simulation is then using to create the magnetization for each voxel. And they have, I don't know, 25 different data sets. Okay, and if you scroll down here, you also see trajectory. So it would also show you the trajectory in K-space, and that's what we will continue talking about a bit.
How can you see the trajectory?
Just clicking on the trajectory button.
There's trajectory.
Scroll down. Probably it's hidden at the bottom.
It's not. Yes, because it's not.
Yes. There you have to that.
You can access it.
It's hidden there, yes.
You cannot select another option.
Okay, so who of you is familiar with the simple gradient echo flash acquisition? So who did hear the name flash before? Okay. And you probably know what gradient echo based sequences are from the first day. So this is the very, very first sequence that you would look at in an MRI course. So what it's doing is, and you can see that also here in the trajectory, this red area here is actually our K-space area that we want to acquire. Everything else is just helping us to get there. So what's happening is, and we can look at the sequence diagram, we excite our two-dimensional slice, and then our spins are excited, and we think about what do we need to do to get our K-space data. So in the end, we have a K-space, and we somehow want to acquire all the data in there. And then we want to do a Fourier transform and get our actual image. So we can handle the gradients just as helping us to go to different positions in K-space. So we can just read it from left to right. So we start here. We have no gradient after the RF height, but now we introduce a gradient in X direction and in Y direction. So this would be X, this would be Y. We start always in the middle of the K-space center, and then we have these two gradients, X and Y, so a diagonal traveling through the K-space. So we will just end here. Then we have a continuous gradient in X direction, which will lead us in X direction. And why doing that? We have the ADC, so the readout is also called ADC, the readouts being activated. So the actual data being read out by the MR system is exactly this data we're traveling through K-space. And as you see, this sequence is not very exciting because we do that over and over and over again. And you see that only one part of the sequence is changing. The part that is changing is this gradient in Y direction. And that's what you see tomorrow a bit more. So actually the implementation of the sequence, if we look at exactly this kernel, which is repeated with each RF excitation, and skip with the different lines, we see that here in the image, the Y gradient is changing for each line index. So as going throughout the sequence execution, we change the amount of gradient moment applied to the y-axis, so that for the next line readout we end here, readout for the next one we end here, and so on. And that way we can then acquire all our lines in the image. And if you look at the whole sequence, you actually see that you start in a negative direction, you end in a positive direction. So going from zero, so the center, start here, end up here, and with each excitation you get one line readout. This costs some time because you only with each RF excitation can acquire exactly one line of K-space. Yes?
Can I ask a question?
Sure.
What was the function of the last pulse in the red column?
Yeah, that's a spoiler gradient. So, and you can also see exactly what's happening in this picture. So this picture basically from here to here shows exactly what I was drawing here. But then after reading out the line, we still have some signal left. So what we do is we call it spoiling. So we spoil it. So we do a complete dephasing of our spins, so that we don't have any signal left. And that's just done with a very, very, very small gradient that just pulls our signal all over the place to wherever not we want it to have, but to whatever place where it's not interfering with the next RF excitation. So then we can excite again and to the negative version of our field. If we would not spoil, we would have signal from the previous excitation interfering with our next image. Yeah.
You are not in random also.
Sorry?
It's not really random, it changes with Y also.
Oh yeah.
What's the goal?
Doesn't really matter. So, I mean, of course, you do the same. So you dephase the Y signal But the important thing is that you dephase it in one direction. So in this case, it's dephased in X direction, so spoiled in X direction, and then that's fine. So we could also, but why should we do it randomly? Because randomly would still have the constraints that we can only do it in that direction, because if we would spoil it back, it would again interfere with our image. Also, it's looking a bit nicer then. Jörn, do you already have something to show for the flash sequence now?
Yes.
Yes, okay. Then we can have a look at how this works on the reconstruction side.
So, ist das diese one? Is there? Yeah. So as I promised, we will have a quick look into more detailed reconstruction operations which happen on real MR systems. So what you usually see is this Fourier transform relation between the acquired K-space data and the image space. But as you can imagine, this is not what is actually happening on actual systems, because there's a lot of data processing involved, and you can't, in almost no case, you can't simply apply a Fourier transform and you get your image back. So fortunately, the flash sequence, as Dan showed us, is quite simple, so it will acquire K-space line by line. So at least you end up with a somewhat reasonable K-space matrix in the end, but what you see is that it looks a little bit stretched into one direction, and this is exactly what we already saw. So we talked about this aliasing artifacts, and that MR systems usually apply a twofold oversampling in the readout direction, this direction. So this is what the data you acquire during one of those readout gradients, and then you step through K-space in that direction to acquire one additional line, line. So this is acquired in the readout direction with half of the K-space spacing and the phasing coding direction. This results in a field of view which has double the size. So what you would need to do if you want to get your real reconstructed image back is to cut your field of view by half. That means you just simply cut off this edge and this edge, or you would resample this K-space data to half of the size in that direction. And if you do that, you basically get what we already saw. So you get rid of those oversampling artifacts. And then you basically need to apply your Fourier transform, and then you're finished. So for the flash sequence, it's actually quite easy on how to get the real image back from data or raw data that you get from your scanner. And yeah, actually you should be able to produce these aliasing artifacts from the front end. So Daniel might be able to show you how. So you just need to decrease the size of your field of view, and then you should, in principle, see that you get aliasing along the phasing coded direction, but the readout direction should not suffer from that artifact. So
exactly. And the good thing is that everything that Jörn tells you is running in the background. So normally you do a simulation, then you get some raw data back, and you have to think about what to do with that, write a Python script and run the reconstruction. Yeah, I just send it to Jörn and get the nice document back. So we have this quick action button here, which can give us a, whoops, I hope it's a bit better in terms of resolution on your computer, but we can guess that it shows protocol window there. And this is actually the exact same parameterization that you could have at the MR system. So if we go to geometry and just cut our field of view in half, for example, so to 128, we see that these values were changed, and if we apply the protocol, we can run the simulation again, and I actually need to send it to one of my MR systems. And what you can see is exactly what Jörn said. So we squeeze the field of view, and we, in one direction, so the phase encoding direction, we get this enfolding artifact, which is also correctly simulated in the simulation environment. So if you, this protocol window, by the way, can stay wherever it is, and in each of the different views of gammaSTAR can just be used, and it's interactive with the sequence. So if you just change the repetition time, I don't know, from 10 to 20 and apply, you directly see in the MR sequence how it was changed. And also, I don't know, just changing the repetition time, doing the simulation again, we also hear it. That it's now more time between Alpha pulses, so it takes more time to acquire the whole K space. It sounds differently, and still being simulated. But okay, I did not change the field of view back, so we still have the unfolding, but you see the difference in contrast just by changing the timing parameters, as a radiologist would do in front of the MR system. So if we put something like a repetition time of 0 in there, that would not work from a timing perspective, and apply, it would accept that. But we have two windows. One would be the tests, and we can perform tests that would now show, okay, the repetition time seems to be too short. So that will not work. We can put that back, check again, and now it all looks fine. So it gives you some hints about what was going wrong with the protocol. So let's jump to the next more complicated sequence. So from the very simple rare flash sequence, we will go to the rare sequence. Who heard the term rare before? Rare. R-A-R-E. TSE. Turbospan echo. Rare is the, I think, Philips term for turbospan echo. Turbospan echo is the name by Siemens, but the original publication was named rare. And it's for rapid acquisition with refocused echoes. Okay, so looking at that sequence, just again, first thinking about, let's just first hear the sequence as it would sound at the MR system. So you see it's some kind of a pulsed sequence, so we have some waiting times and some things going on in between. If we look at the sequence diagram, and by the way, you could also right-click and add graphs. So we also show the different gradient moments, slew rates, etc. For simplicity, we per default just have the typical 5 axes for MR sequence representation. So who said that he or she knows the TSE sequence? Okay, it's a combination of a flash sequence with spin echoes providing a faster acquisition. So what we did before was an excitation pulse, and then we read out a single line. So what I told you before is that it takes some time to always wait for the next RF excitation to acquire a single line. There were some people thinking about that, how to accelerate that. And one way would be to work with spin echoes. So I'm pretty sure that Matthias already introduced spin echoes. So we have a 90-degree excitation pulse. Then we use a spin echo to create an echo, which is exactly at the position between the duration between here and here. So the same duration, we have all these spins aligned again for our spin echo. And that's a simple spin echo acquisition, but we can go a bit further and do that over and over again, so that we have our excitation and refocusing, we get an echo here, and that signal that's here will get refocused and being read out here again and again and again. And with that, we can, with a single excitation, read out multiple lines. So we excite once, and then, depending on which lines we choose, can read out 1, 2, 3, 4, 5 lines. This is, of course, restricted by relaxation processes. So there is the transverse magnetization, which is quite high after the excitation pulse, but then it decays, and we can only do that as long as we have sufficient signal. It's quite important to think about which lines we should read out at which position. So if we have a look at, whoops. Okay. I can also draw that. So as I mentioned, we have a change in signal intensity. So we have a signal decay. So this readout experiences the most amount of signal, and then it decays up to here. So if we just read out our K-space from top to bottom, we say we have a first excitation pulse, a readout, and then we read out the first 8 lines. That would mean that here we would have the strongest signal, and it would decay until here. And if we then continue, we can think about the next excitation, first line being here. So we, at that position, have a very, very strong intensity jump in K-space. And we also have that here, here, and here. So we'll introduce 1, 2, 4, let's say 6 different segments in K-space. So we introduce a frequency in K-space, which would lead to ghosting in the spatial domain. In this case, it would lead to 6 or 8 ghosts overlapping the actual image. What we normally would do is to not acquire these lines, but to start with the first line and then go by segments. So we define these segments and we acquire with a single excitation always the first line in the segment, the first line in the next segment, the first line in the next segment, and so on. And if we go to the next excitation, the second line, second line, second line, second line. And this very much reduces the maximum frequency intensity jumps in the K-space, smoothing out the signal through K-space, getting rid of the ghosts, and let's say smearing the intensity differences throughout the K-space, resulting in hopefully nicely looking images, but there is something going on here. So if you followed along, you also see that on your devices. Any idea why this would happen? And that's a complicated question because we also discussed about that when seeing it.
Yeah, but think about the artifacts that we saw on our report. So it's related to one of those reasons for ghosting artifacts that we discussed about. Because of more appropriate behavior.
Yes? No.
Yeah, so it's basically related to the fact that you require, although you have a better segmentation in case bases than you just explained, you still require these different segments of case-based data not in the steady state of your signal. So this is exactly the situation which I explained, like you require a first segment where you have full magnetization available. And after that, after you excited that and you did not wait long enough, so not the full magnetization has relaxed, you don't only have a fraction of that available for your next segment. So that introduces like signal intensity shifts. And if you then think about this concept of case-space being split up into different segments, which will introduce ghosts, so which would cancel out if the intensity is the same, they won't cancel out in that case. So if you want to get rid of that, you either make sure that you have preparing scans for multiple measurements, which would introduce a steady state of magnetization, so you only have a fraction of magnetization, but it's the same fraction for each of the case-based segments, or you make your TR, so the repetition time, really long, which makes sure that all the magnetization has relaxed, and then you also have the same amount of magnetization available for each of the segments. In both cases, you should basically get rid of the sensitivity.
So I decided to do the first one, I think it was. So having a preparation. Yes.
Where did you get the
Yeah. I just show it again. So open up the protocol window, and then under special, there is the measurements parameter. So if you increase it, you will do exactly the same acquisition again. So if you increase it to 2, you will do exactly the same acquisition twice. And we see nothing changed. But if we go through the images, so now we did 2 acquisitions, we see that the second image is already in steady state. So you can, right here with the arrows, just click through the different images. And this is because if we look at the, let's say the transverse magnetization, which is 0 at the start, and with our RF pulse, well, let's say be at 100, and then it decays, and then, oh no, let's do it the other way around, let's go with the longitudinal. So we have the longitudinal magnetization in equilibrium state, we excite it, and then it's basically 0 with a 90-degree excitation pulse. It then recovers. But at some point, we want to excite it again. So we could wait for it to be back at the equilibrium state, but that would then we would need to wait for seconds. But we want to be fast, so we just say we measure again after 500 milliseconds, exciting this again. And then it's again recovering. And at some point, the process of relaxation is exactly the same for each repeated measurement. So the first, second, probably also the third segment that we acquire just introduces artifacts because not being in steady state. But with the second measurement, we already, for the first measurement, are in this steady state scenario. So we start in steady state and get a clean image. The same would work, as Jörn said, instead of going with 2 measurements, to just increase the repetition time to 2 seconds. 2 seconds. That might be a quite long measurement, so I will not send it to the scanners. But that should also give you a good looking image without this artifact. Not yet. Okay, so if you want to do that, you should go for 5 seconds. So if we do that, it should be definitely fine afterwards. So we will go for 5 seconds. Okay. So you can see the result, and then you will show what he needs to consider in the reconstruction. And there it is. So with 5 seconds of TR, we get enough time to have the relaxation right back at the top, so at almost equilibrium state, and then we have a steady state right from the beginning, because we wait for a long time.
Yeah, one point I didn't understand, like what you said, there's not enough time for relaxation. Sometimes versus the domain to domain. But why we are not doing, like you said, there are segments in the case space, so we can selectively extract that segment only, and therefore we know that those on the other part. Why we are, I couldn't understand.
Oh, no. So that's the first one is really the signal decay within your readout train, your signal excitation. But your TR defines the excitation of exactly the same slice. So it wouldn't change if you select another segment, because you excite the whole slice. So it's a slice selection. And
we are not exciting only that segment.
No, you are exciting the whole two-dimensional slice.
But the morning session, we get only data by getting the magnetization from transfer to the domain, and we are getting a split pattern and break pattern. So it's not possible to have only like magnetization on the transverse domain for only the first segment of the gate phase and then the second.
No. Of course, you could think about trying to somehow dephase everything in that area, but that would be way too complicated.
Yeah, so as Daniel already explained, so for the rare sequence, it's a bit more complicated or the system actually does a little more complicated reconstruction process. So Daniel explained that in that case, you won't simply acquire case space line by line, but you have those different segments, and you simply acquire like the first line in the first segment, and then the next one would be like this, the first line in the second segment. So if you do that at your MR system, basically all acquired data will be sequentially stored in a matrix, and you end up with something like this. And if you would apply your Fourier transform to that, you won't get your image back. So this is not how you could deal with the raw data that you get from a system if you use the rare sequence. So basically, that's what Daniel just explained. So you have different types of readout patterns. So what you need to do is basically first to remove your oversampling again. So you would just decrease that by half by resampling or by Fourier transform and removing not needed part from the view. And then you have from your gammaSTAR sequence, it encodes basically where each of these lines would belong in case space. So what you would need to do is a line reordering, and this would be quite complex. If you don't have that information, you need to figure that out based on this raw data which you got. But fortunately, gammaSTAR tells us where each line belongs to, so you would need to remove the oversampling, then resample everything. So this, of course, belongs to the center, and some parts or some lines with lesser magnitude belong to the outer parts. And if you do that, you get back your actual case space which you want to use. And on this case space data, you can finally apply your Fourier transform to get back that image. But it's not like you can directly use the data from the scanner to do a Fourier transform to get the image back. So this is basically what your MR system would do in case of such a rare measurement, which you might want to do, and which is also applied in this scenario with the simulation and this reconstruction server in the background. Yeah.
Okay, we just saw what's going on in the background because this workshop notebook crashed because it would require 150% of the CPU available for this simulation. So there's a lot going on in the background, which is also why for release it would be would somehow need to be one like centralized where it's really having the resources. So we will go to the next one. Okay, we'll go with the EPI sequence. That might take half a minute to load. So you used this 2D EPI readout already in the yesterday and in the morning a lot. So that's maybe the classical way to acquire fast images. So a typical EPI readout would last 60 to 100 milliseconds. If you multiply that by 32 slices to get full brain coverage, that would mean 3 seconds. And then there are acceleration techniques that would bring that down to 1 second or 500 milliseconds. So it's one of the fast acquisitions with very low resolution to acquire fast images, often used for functional MRI, where you, with a high temporal resolution, want to acquire a lot of images after each other to see physiological changes. Sorry?
I can see the case-based result.
Oh, we should be able to select the trajectory. Yeah. Oh no, case-based is currently not transferred. There. Because this is an endpoint to gather the type data to also provide the raw data as a download. So that's a standardized ISMRMRD raw data file. It's really downloaded. And the button for the this is select over because before that we can show. I have the same one. Okay, so you probably already know this sequence type. It's an EPI sequence. We have this zigzag readout type. So if we go from left to right, we for now just ignore this one. We have our excitation, our slices being excited, and then we have this so-called pre-phaser. It's exactly the same as for the flash sequence, bringing us in our case space from the center towards the outer edge or corner of the case space. And then we have this zigzag pattern for the x direction and these little case splits for the y direction. If we zoom in there, we can see that we will next travel through case space, then have a short, small phase blip, which brings us right to the next line here, and then we need to reverse the sign of the gradient moment to travel back to case space, and doing so we can acquire the whole two-dimensional case space with a single excitation. implementation. And you don't need to follow what I'm now doing, because that's something we will do tomorrow, but I just want to show it to you. If we disable the phase correction, and Jörn already talked about the phase correction before, so now it's really a simple API sequence. We will probably also get rid of the phase saturation, so that where is it? We have the most simple API sequence. We will go to simulate that, and maybe we can also hear how fast it is. That was it. So maybe again, in case you missed it. So it's 100 milliseconds. And now you probably already know what this is, because exactly that was shown by Jörn. So what do we see? Yeah. So Aliasing, Nyquist ghosting. So exactly the type of ghosting that we see with the EPI images. And luckily, we also simulate that. If you look very closely, we can see that each second line, or all these lines are not really aligned. So can you actually see that? So we have this line starting here, and the next line starting a bit more to the right. This again here, this a bit to the right, and so on and so on. So we introduce a frequency which is exactly changing each second line, which will then in spatial domain result in exactly one ghost perfectly aligned with half of the image, or half of the field of view. What we do to get rid of that is to have something called phase correction in the sequence. I will just enable it again. Do the simulation. And this is this part here. So these are calibration measurements that we do for reconstructing the image and getting rid of these phase differences. You see, if they are in there, we get a perfect image. So what these phase scans do is, without any gradients, you see maybe because the center line is a bit thicker, because in these phase correction scans, we acquire the center line 3 times in both directions and calculate the phase difference between these lines. And this phase difference is then applied to every second line in k-space, shifting the lines or aligning the lines toward the k-space. I think that Jörn will show a bit more about what's happening in the reconstruction there.
Yes. So, as Daniel already explained, the API is a bit more complicated than the sequences we saw before. So, because we have these reference scans which we need to get rid of the Nyquist ghost. So, if we just do an API scan at an MR system or with the simulator, which we have here, we end up with raw data which looks like that. So you get the portion which looks somewhat like case-based data, but you also get some strange data here. And if you just apply the Fourier transform, you get a really strange image. So this is definitely not what you want. But what you see there is exactly what Daniel explained. So we have 3 lines of case-space up front of the acquisition. This is your reference data, so you acquire the central case-space lines. This is why you always have like a quite intense signal in the central part. So you acquire the central data line, like up, down, up. And based on the shifts that you can estimate between the up and down lines, as this is basically the same line, you can estimate how this API shift between even and odd lines looks like. And this is then applied to the actual API data which you sample time after that. You also see some strange line in here. This is basically something that is also included in the sequence, which is for frequency correction, because we have, after some time, you get gradient heating and stuff like that, and based on such a reference scan, you can somewhat correct for that. So this is also integrated in the sequence. So yeah, this is basically what I just explained, and what this allows you to is to then have like your uncorrected case space which has the shifts between even and odd lines that you directly see that here everything is nicely aligned and the lines are away. And this also allows you to get rid of your ghosting artifacts. So this is why you definitely need that in your sequence. So one other thing that so let's assume that we apply this correction, so we get rid of this first part because we don't need it anymore. What you will then see is that you still get some strange small ghosting artifacts in these parts. So you're still at the point where you simply can apply the Fourier transform. This is because the system acquires even and odd lines in an up and down fashion. So you would go up, then step one to the side and go down, and step one to the side and go up, and so forth. And internally, the system will always store each line the same way. So you would store like the up lines by filling the matrix on this side, and the down lines also by filling the matrix on this side, so the internal memory. So that means before reconstructing your image, you would need to flip every second line to really correspond to the actual direction, how it was measured. And so I think, I don't know, yeah, I think it's basically that. If you do that, then you finally get your real case space, how it should look like. And then in the end, you can finally apply your Fourier transform to get your final image. But you see that for this case, for such an API sequence, although the concept is quite simple, there are already quite a lot of correction and reference steps involved before you get the image. In principle, this is also only half true, because for API to be more efficient, you can also introduce something which is called ramp sampling. So instead of only sampling data at the plateau phase of your readout gradient, you would also sample data during the ramp phase of your gradient. And this would require you to regrid your data to an evenly spaced case-space grid, and this is quite common to be applied. So this is also integrated in here directly or in the reconstruction. But yeah, if you would not do that, you would basically end up with images which look a bit distorted. Yeah, I don't know if yeah.
So yes, luckily we do that, so we can show exactly that. To follow that would help to right click and toggle the vertical marker. That would help to find the alignments between the different plots. If we zoom in into the EPI readout, we can see that we start the readout already during the ramp up duration of the gradient. So normally the conventional EPI design would start the readout here, because then I know I have a constant gradient, I have a constant sample rate, and I do not have to consider it in the reconstruction of the image. What we do is because we want to be a bit faster, we already start here with reading out the data and end here. So we also read out data during the ramp of the gradient, which that means is, and I try to show that. So we have the case space. Let's just consider we are acquiring a single line in case space. If we start sampling or reading out the data with a specific sample rate, so what's happening is that with a constant velocity we travel through case space, and with a constant rate of sampling frequency we acquire our case space samples. So that would mean that with a constant velocity and sampling rate we get equidistant samples of our case space. What happens if we already start when starting the readout on this ramp is that here the gradient is not as strong as it would be here, so we travel slower through k-space. We start here, we have the same sampling rate of our readout system, but we travel more slowly towards the beginning and the end, which would mean we have the ramp up phase, and then we are faster, we have the same velocity as before, and we slow down towards the end. So now we don't have equidistant sampling anymore, but we have a more dense sampling here, an equidistant sampling here, and a more dense sampling again here. And that's exactly what Jörn has to consider during the reconstruction. I don't know, you probably do a regridding of these samples, so putting it back on the regular Cartesian grid, even though they are not acquired in equidistant samples. And for that, he needs to know exactly where these samples are acquired in k-space. And we deliver this information to the reconstruction server, so it can just shift the position of these samples. Okay, so now we can also, let's go to the sequence diagram and look at, open this protocol window and look at how such an EPI sequence would actually look like when it's used at the MR system. So one, in this case 50 millisecond, a single 2D slice readout is probably not very exciting. So we first of all go to the geometry tab and increase the number of slices. I don't know, maybe to 20. So now we see 20 2D EPI acquisitions, each for a single slice, covering a whole volume, which could be a whole brain scan within, in this case, exactly 1 second. And we would do that, and I don't want to stress these workshop computers, but let's just do it 2 times. And we can see that we get this direct feedback of the sequence. We can send it to the mock-up systems, and that's more like you would experience an EPI sequence in reality.
I would expect some.
Was thinking a bit.
Yes, if we would have.
So one step further in this direction of acquiring very fast images, but still having this EPI-based readout would be the GRASE sequence, which, okay, now or after the GRASE? Okay, would be the GRASE sequence. So if you select the GRASE sequence, it almost looks identical to the EPI sequence with one very little difference. We just give it some time. So the initial loading takes some time because the calculation of the MR sequences in the background is quite complex. And we need to pre-calculate a lot of things so that when working with the sequence, it's all smooth. So let's wait for it. You maybe, oh, okay. So this is a so-called 3D GRASE sequence, which is our favorite readout for arterial spin labeling. There are other readouts being used, but we very much like the 3D GRASE.
So white paper recommendation.
See? Who wrote that white paper? So if we have a look at this sequence, we see these parts of EPI readouts. By now we know that such a readout would give us a two-dimensional slice. It's called a 3D GRASE sequence, a 3D sequence, and GRASE stands for gradient and spin echo. A typical conventional EPI sequence would only be a gradient echo sequence because we don't have a refocusing pulse creating a spin echo. So we combine that. We have a heavy pulse, a refocusing pulse, and get after exactly the same duration a spin echo and place our caseless center at exactly this position. And now we remember that there was this turbo spin echo or WARE sequence where we just utilize the signal that's still the signal that's still there, refocusing it again and getting a second echo here, a third one here. And the little trick that we are doing is that we acquire a 3D volume. So each of these EPI readouts is actually a 2D slice. We refocus the signal and acquire another slice, which means these pulses also need to be 3D pulses exciting a whole volume and not a single slice. So we excite a whole volume, we get the spin echo, read out a 2D slice, we get another spin echo, get another slice, and with that get our whole 3D volume. And in this case, 1, 2, 3, 4, 5, 6, 7, 8. A volume with 8 slices in, I don't know, 400 milliseconds. We can also send that to the system. And this is exactly the readout we use for arterial spin labeling.